Good evening, everyone. We are going to initiate session 6 that is correlated with radiobiology and biodosimetry. The first speaker is Dr. Ruth Wilkins. She is a research scientist at Health Canada, Ontario, Canada. And she is going to present the WHO BioDoseNet, the third survey preliminary results. Ruth, the floor is yours.
Okay, can you see my screen?
Yes, perfect.
Okay, and you can hear me, I guess. Okay,
Yes.
Excellent. Well, thank you for inviting me to give this summary of the WHO BioDoseNet. I'm going to just give an introduction to what BioDoseNet is, and then I will present some preliminary results from the survey. So for those of you who aren't familiar with the WHO BioDoseNet, it's an international network of biological dosimetry laboratories, and it brings together the experience of labs to harmonize protocols for standardization. We work on building capacity of the laboratories. We try to coordinate exercises between members of the laboratory. We develop guidelines, foster collaboration, assist with training and education. And we also, the aim is to be prepared to assist during an emergency. So this is just a timeline of the evolution of the network. So it started as just an idea back in 2006 at one of the EPR BioDose meetings in the US. And you can see how we have grown through the years. We've had several meetings, our first meeting in the US, second meeting in France, third meeting in the Netherlands, the fourth meeting in the US, and then our fifth meeting in Germany in 2018. And we've conducted several surveys over the year. This is our third survey. So we had one in 2009, one in 2015, and now this survey. So you can see some nice pictures here of all our meetings over the year. This was our 10th anniversary that we held in 2018 in Germany. And you can also see the growth of the network. We started with 27 members back in 2018, and now we're up to more than 80 members. So the survey that went out, we sent out a survey in November of last year, which was closed in February of 2021. It went out to all participating BioDoseNet labs. And you can see the comparison over the years of the surveys. We had more and more labs invited each year. In 2015, we had an extremely good number of labs completing the survey. Unfortunately, this year we only had 74% completion rate, but still a nice number of labs, 62 labs that completed our survey. So to keep consistency across the years, we've tried to keep the questions fairly similar from year to year. We ask questions on capabilities, capacities, procedures, quality assurance and quality control, and what kind of needs the labs have. We're currently analyzing the data, but I'm just going to give you some preliminary results here. So this is not for distributing or quoting because it's still quite preliminary. I haven't had a chance to do the full analysis on it yet. So this is a map that shows the labs that responded to the survey. So each of the red dots indicates one survey, one lab. The size of the dot, or if there's a number inside the dot, will indicate about what their capacity is for immediate emergency response. So there are some that are just in progress, or they don't have a capacity, going right up to those who stated that they could analyze over 100 samples a week. So you can see it's nicely spread out over the globe. The other thing that is shown on this map are the networks that have formed. So there's a North American network, a South American network, the Latin American network. There's a Chinese or an Asian network, and then the European network here. And this, one of the biggest changes since last year is that this Asian network is new since the last survey. There are quite a few new labs also that have joined the Latin American network. So just to give you a very brief overview of some of the results of some of the questions that we asked. So we asked about how many labs, how many people each lab had for doing different processes. So for culturing, scoring, and data analysis. So you can see the results here that most labs have 2 or 3 staff members that can do each of these 3 activities. I think somebody needs to mute their microphone, please. And you can also see that over the years, there's been little change in the staff capacity. Most of the staff do culturing and scoring, fewer staff do data analysis. And these are just the averages over the years. So you can see that there's really very little difference on average on staff capacities between the labs. Then we looked at the capacity for the dicentric analysis, which is the main method that's used in most of the labs, and how many samples could you analyze if you were scoring for triage quality scoring, looking at 50 metaphases per sample. Oh, I'm sorry, there's no axis on the bottom here, but you can see there are lower numbers for a week, and then of course it went up per month, and this is up to over 800 is this largest bar. And then you can see on the table the change over the years. You can see in 2021, in this survey, there's a huge increase in the capacity, although this was really due to just one lab who was who reported that they could do 2,500 samples a week or over 10,000 a month. So that's really skewing that data. If you take that one lab out, then the numbers are actually quite similar from one to the next. This graph just shows the different techniques that are available in each lab. You can see the dicentric assay is the most common, with all of these others being less common. And then this graph shows you which methods they actually have a calibration curve for. And you can see that there's very little difference in the number of labs having each techniques over the 3 surveys. However, so this is in percentage. However, the percentage of labs that have calibration curves seemed higher in the last survey than it did in the 2021 survey. As far as I can see, the explanation for this is that in 2015, there was a huge increase in labs that were part of the European network, which is a very well formalized network. And then this year we had some newer labs that were less experienced and have not had an opportunity to develop their calibration curves. This graph is one that I think is very promising. It shows you the different labs that are involved in networks and exercise participations over the 3 surveys. And you can see there's a huge increase in labs participating in several of the networks. If you just look all the international networks together, there's quite a large increase in the number of labs participating in networks. And also an increase over the years of the labs participating in different exercises. So I think this is really great news for our network. So for the first time, we asked a question about pandemic response, because of the time that we're in with, as we're all living through this COVID-19 situation, we thought we would ask how the labs would be able to cope during a pandemic response. So we asked questions like, has your laboratory considered the changes and challenges associated with COVID-19 or similar crises? 53% said yes. If there was a non-radiation emergency, would the lab be able to accept samples? 40% said same as usual, 42% said a smaller number, only 18% said they would be unable to accept samples. And do they have policies for accepting blood that may be contaminated with another disease? Half of the labs did. And did the labs have any expertise that would be able to assist with diagnostic testing? And only a quarter of the labs would be able to help with something like COVID testing. This is just a summary of the priority needs that were assessed by the network. And I have more details on that on the next slide, identifying the gaps that they identified that maybe the biodosimetry network could help with. So the main gaps identified were assistance with interlaboratory comparisons. Some labs don't have access to ongoing comparisons, knowledge sharing, training, international research collaborations, collaboration curve development, financial support, emergency preparedness support, and standardization and harmonization of methods. So just to summarize with some successes and challenges, that they were continuing to grow. We have gone from 27 to more than 80 labs. We have regular meetings, and this has really built the community as we all have been able to come together, except now, but previously come together, share experiences. We've had some activities, web-based scoring exercises, shipping exercises, establishing an image repository, using the image repository for training. But one of our main challenges right now is our website that needs updating and rebooting, and also just trying to fill all the gaps and the needs of all the members who come from labs of various levels of expertise. So these are challenges we are still working on. And I'd just like to acknowledge Janat, who made this all possible, and my two colleagues who've helped, David Lloyd and Natalie Maznik in the Ukraine, and all the respondents to the survey. Thank you.
Thank you so much, Ruth, for this important presentation. And it is important to highlight that this is the first time that the condition of the pandemic COVID-19 is assessed and as a crisis in the laboratory. And it's interesting to see also the higher networking that is placed in this survey. Thank you so much. Now, the second speaker is Dr. Davis Andersfelder. I'm not sure how to pronounce it.
Perfectly.
Sorry. He is responsible for statistical analysis and development of statistical methods in the Department of Biological Dosimetry at the Federal Office of Radiation Protection, BFS of Germany. David, the floor is yours.
Yeah, thank you very much for the kind introduction. I try to share my screen now. Can you see my screen?
Yes,
so
perfect.
Perfect. So go to presenter mode now. Yes, hello to everyone, and thank you very much for the opportunity to give this presentation today. And what I'm going to show you today are some results from a joint BioDoseNet and REPAN field exercise performed in Lund, Sweden in 2019. And I'm going to show you the results of the biological dosimetry based on dicentric chromosomes. So just very briefly on the background, this was an exercise performed under field conditions, and as I said, it was organized by the European Network for Retrospective Dosimetry, RENEP, and by Eurodose Working Group 10. And the aim was to simulate several exposure scenarios, including close, distant exposures, partially shielded exposures, heterogeneous exposures, and lateral exposures. And a further aim was to validate and compare variable methods of physical and biological retrospective dosimetry. And for the RENEP member laboratories, this was an interlaboratory comparison, so we could really compare results between labs. And the members were asked to score dicentric chromosomes in 500 cells and provide dose estimates in 95% confidence intervals based on the dicentric chromosome assay. So we had 18 participating laboratories all across Europe, more or less. And these included hospitals, military, radiation protection agencies, and universities. And so first we took blood samples. This was from one donor, and each blood tube included 7 milliliter of blood. And these blood tubes were then put into thermos flasks, which were filled with water at approximately 37 degrees. And each thermos flask included 1 to 4 blood tubes. And on the blood tubes, we put 3 RPL reference dosimeters at the top, middle, and bottom position. And we had two irradiation setups. This is the first setup where we had Phantom 1 and Phantom 2. Phantom 1 was to simulate a close exposure, and thermos flasks were located at the left tip and left shoulder. And Phantom 2 was to simulate a partially shielded exposure, and it was in an angle of 45 degrees to Phantom 1. And it included two thermos flasks at the left and right tip, and the exposure time was 1 hour. And the setup was published in a recent publication in Radiation Research. And the second irradiation setup was with phantoms P3 and P4. P3 was to simulate a distant exposure with approximately 1 meter and 10 away from the source, which was a iridium source. And Phantom 4 was located in a 45-degree angle to the source and was supposed to simulate a lateral exposure with thermos flasks at the left and right tip. And the exposure time here was 2.5 hours. And now I will show you the results of the biological dose estimates compared to the RPL reference doses, and you see the results on the right-hand side in these box plots. And on the left-hand side, you always see the positions of the thermos flasks associated to the dose estimates on the right-hand side. The RPL reference doses are shown with orange crosses on the right-hand side, and the black dots within the boxes show the dicentric chromosome dose estimates. And each box shows one blood tube. And here, for example, we had this thermos flasks here on Phantom P1 on the left tip, which was the close exposure, which also had the highest doses. Within this thermos flask, we had dose estimates for three blood tubes. And we see that the biological dose estimates correspond quite good to the RPL reference doses, but are somewhat systematically lower than the reference doses, and I will explain this later on. And what we also see is that there's some heterogeneity between the tubes within one thermos flasks for the RPL reference doses and for the biological dose estimates. And this is probably due to due to the positioning of the tubes within the thermos flask. So maybe there's some partial shielding also going on. And the second highest dose was here on Phantom P4 at the left tip, also quite close. And we again see this heterogeneity, and we again see some kind of systematic underestimation of the biological dose estimates. And for the lower doses, here, for example, on Phantom P2, Phantom P3, and so on, we just very briefly go through them because we don't have very much time. We see a very nice correspondence of the RPL reference doses with the biological dose estimates. Only for this Phantom P4, for the lateral exposure, it's not so perfect, but here we had only one lab providing a biological dose estimate. And this is due to the design of the experiments. Due to this, we had only one dose estimate here. So just summarizing what I just said to you, for the low dose samples, which were below half a gray, we had a very good agreement of the dicentric chromosome dose estimates with the reference doses. And what we also see for this sample P1b, which was about 100 milligray, it was very difficult to distinguish from the unirradiated control. That's just due to because it's close to the detection limit of the dicentric chromosome assay for 500 scored cells. And for the higher dose samples, which were above 1 gray, and very close to the source, we saw a good agreement of the dicentric chromosome assay estimates with the reference dose estimates. We saw heterogeneity between tubes within one thermos flask for the RPL and dicentric chromosome dose estimates. So we could really resolve this heterogeneity we see for the RPLs also with the dicentric chromosome assay. And for the higher doses, we see a systematic underestimation of about 200 to 250 milligray based on the dicentric chromosome assay. And when we now look at how many laboratories were within, let's say, 250 milligray or 500 milligray, or how many of the estimated 95% confidence intervals included the reference dose, we see that this is almost perfect for the low doses. So 90 to 95% were within plus minus 250 milligray. And it's not so perfect for the higher doses due to the underestimation I mentioned. So what we looked at then is what might be the reason for this systematic underestimation. And as I told you, the exposure time was 1 hour for the first setup and 2.5 hours for the second setup. And for the initially provided DCA dose estimates, we did not consider the exposure time for the estimates. So we thought maybe the production time might, if we consider this, this might correct the underestimations for the doses above 1 gray. And on the left-hand side in these box plots, you see the acute dose estimates in the white boxes and in the gray boxes if we consider production time. And here for P1A and P4A, you see if we consider production time, the dose estimates are closer to the RPL reference doses. So if it's close to this dashed red line, it's closer to the RPL reference doses. And also we could increase the number of labs that were within plus minus 250 milligray to 70 or 80% for these 2 samples. So the underestimation might be due to the protected exposure time. So in summary, this was a field test with many sources for uncertainties. So typically in interlaboratory comparisons, we have very controlled laboratory conditions. And here this was really performed outdoor and a lot of logistical problems here. But nevertheless, we found very homogeneous results between RENAP labs under very difficult conditions. If you consider exposure time, we corrected for most of the systematic underestimation for the higher doses. All of the participants were able to identify the high dose or low dose samples. And we also saw intra and intertube heterogeneity for the reference doses. And this could also be resolved by the dicentric chromosome assay. And we think this is due to the positioning of the tubes within the thermos flask that partial shielding might happen here. So again, even under field conditions, the RENAP laboratories are able to provide very reliable DCA dose estimates and very valuable information to reconstruct the exposure scenario. And I'd like to thank all the organizers and participants from RENAP and DIODOS. And I was also asked to include a slide about research gaps. And we think that networking between international laboratories is very valuable tool to provide dose estimates in a large scale exposure scenario, and should be further developed. That this is important. And methods for retrospective dosimetry should be further improved. And it's also important to perform regular interlaboratory comparisons to improve the performance of members of a lab. And what we want to do in future from the results we got from this exercise is to combine variable methods from biological and physical retrospective dosimetry. And we also think that more research is needed on statistical methods for dose and uncertainty estimation and on characteristic limits, especially for complex exposure scenarios. And certainly further education and training is always required. Okay, thank you very much. And I stop sharing my screen.
Thank you very much, David, for your interesting presentation. Yes, you are highlighting the importance of retrospective dosimetry and in a multiparametric approach that is very interesting for the networking. Thank you so much. Now we are going to present Dr. Andrei Bushmanov. He is the first deputy director of the Federal Medical Biophysical Center in Moscow, Russia, and he's a specialist in radiation protection and radiation medicine. Dr. Bushmanov, the floor is yours.
Yes, I am ready, but I need my presentation into the screen.
It is on the screen.
You can see it?
I can see it. Now, yes, it's mine. Dear colleagues and friends, I want to tell you about our new approach to biological dosimetry based on analysis of DNA double-strand breaks. Next slide. As you know, now we have some biological tests, some of them traditional cytogenetic tests, sensitivity about 100 and 200 milligray fish, test about 300, 500 milligray. But some people from atomic industry, Chernobyl liquidator, have the total dose less than 150, 100 milligray. So this method is not really used, and these people for the indication their doses. Now we try for last 10 years in our laboratories, in our center, we use DNA double strand breaks method, shortly DNA DSBS. Next slide. The most important characteristic of radiation-induced DNA damages is complexity and clustering. Among the DNA damage caused by ionizing radiation, DNA double-strand breaks are most critical for the future function of the cell. Next slide. For our opinion, this method we have three different classifications in this method. The first one, method based on assessing of degree of DNA fragmentation, enzymatic methods, and method based of quantitative assessment of protein involved in DNA DSBS repair. Next slide. The first one, methods based of assessing the degree DNA fragmentation. Pulsed field electrophoresis is the method of fractionation of high molecular weight DNA from 10,000 to 10 million base pairs using electrophoresis in agarose gel under condition of periodically changing direction, pulsed electric field. This method has become one of the key tools in modern genomics, as it makes it possible to estimate the size of large DNA. Next slide, repairs. Next slide, please. The next one is DNA comet assay. Electrophoresis of single cell DNA in agarose gel was the first described by Austin and Johansson, and we see that high molecular undamaged DNA formed the comet's nucleus, and the damaged fragmented DNA migrated to the anode, creating a kind of tail. Next slide. Advantages. Analysis of DNA fragmentation of single cells. Relatively high sensitivity, about 50 DNA DSBS per cell. Disadvantages. The specific of the method for DNA DSB analysis is controversial. It is discutable. Next slide. The next method is enzymatic methods. The tunnel method is specific binding to the third end of the broken DNA strand labeled with biotin or fluorochromes. This binding is carried out by the enzyme desoxynucleotide transferase. Next slide, please. Advantages. Analysis of DNA fragmentation of single cells. Disadvantages is low sensitivity. More than 20 DNA DSBS per cell. Next slide. The next group of method is based on a quantitative assessment of protein involved in DNA in DNA DSB repair. We think that quantitative analysis of the specific focuses is the most sensitive method for the analysis of DNA DSBS and can detect an increase of amount of DNA DSBS from radiation doses in a few milligrams. Next slide. Advantages. Qualitative and quantitative studies of various intracellular macrostructures, in particular focuses of DNA repair proteins. The possibility of a differentiated analysis of heterogeneous cell population by various parameters. High sensitivity of quantitative analysis of DNA DSBS from several DSBS per cell. Disadvantages. Low productivity, no more than 1,000 cells per sample, and high time for macroscopy and analysis, more than about 30 minutes per sample. Automatic systems are very expensive now. Next slide. And now I want to say about analysis of DNA repair proteins using fluorescence flow cytometry. Flow cytometry is the method recording the optical parameter of cells particles in a stream from light scattering and fluorescence signals in stream mode. For the quantitative analysis of DNA DSBS, the most often used is the assessment of the phosphorylated from specific histons. Next slide. Advantages. Rapid analysis of the DNA repairs protein is in single cells is streaming mode, tens of thousands of cells. The possibility of differentiated analysis of heterogeneous cell population by various parameters. Cell size, granularity, fluorescent probes, labeled antibodies to various proteins. Disadvantages. Low sensitivity of DNA DSB analysis, more than 50 DNA DSBS cells. There is no possibility to carry out quantitative and qualitative studies of intracellular microstructures. Next slide. In this picture, you can see dose response curves from immunofluorescent imaging cytometry. Next slide, please. Advantages. Image stream hybrid technology allows you to use the advantages of microscopy and flow cytometry. And disadvantages here, the quality of micro images is not enough. Next slide, please. So this is a conclusion of our 10 work in this area, the work of our center. So the most of sensitive and informative is immunocytochemical analysis of the number of focuses of DNA double-strand break repair proteins. Microscopy and image stream hybrid technology. Quantitative analysis of the focuses of DNA repair proteins make it possible to detect an increase in amount of DNA DSBS at a radiation dose of only a few milligrams. A joint analysis of the specific focuses and make it possible to access not only the quantitative change in DNA DSBS, but also to obtain important information about the correctness of their repair, which is extremely important for predicting of long-term consequences of radiation exposure. We think this new approach, why new? It's not new. We know this method for many last year in the world practice, but in our practice, it is new approach. We think this new approach to radiation biodosimetry will be used for accessing the exposure doses in nuclear workers, as well as the population affected by the consequences of radiation accidents. The next slide, please. And there are two gaps in radiation biodosimetry. Underestimation of dose from long-term and chronic exposure. The text you can see at the picture. Next slide, I want you attention for the situation with combined radiation injuries. In our practice, we see incorrect radiation dose estimation for combined exposures. This combined exposures, so radiation and some other factors, such as thermal burns, mechanical factors, thermal mechanical factors, and chemical factors. In this case, estimation of biodosimetry estimation dose is not easy. It is a big problem because, for our opinion, we can see a good result, such as a physical dosimetry in these cases. Thank you very much.
Thank you for your interesting presentation and the approach of the analysis of DNA double-strand breaks as a biodosimetry endpoint. Thank you so much.
Okay, as Marina is the next speaker, I will introduce her. I'll take over as chair for now. So it's my pleasure to introduce Dr. Marina Digiorgio from the Nuclear Regulatory Authority in Argentina.
Thank you so much. Well, my presentation is on the Latin American Biological Dosimetry Network, and I'm going to address the quality management system within the network. So the victims of accidental exposure show better chance of survival if they receive medical treatment early. So the increased risk of scenarios involving mass casualties has stimulated the development of tools that would help the medical doctors to treat victims, so that the biological dosimetry has become a routine test to estimate the dose contributing with physical and clinical dosimetry. One of the existing strategies to avoid mass casualties events is to use cytogenetic networks to enlarge the capabilities for rapid triage and reference dose assessment. In this sense, the Latin American Biological Dosimetry Network was established in 2007 in the frame of IAA Technical Cooperation Project, and its mission is to provide early biological dosimetry assistance in case of radiation emergency in the region. And the objectives are to strengthen the service capacities of biological dosimetry laboratories that exist in the region to provide an early biodosimetry response for mutual assistance, but integrated to the national radiological emergency plans. Another objective is to provide support to other Latin American countries that do not have biological dosimetry services. And the third is to work cooperatively and articulately with other international networks. Related to the quality assurance and control in the region, in the LBDNet, it is based on harmonized protocols and also harmonized scoring criteria, mainly based on the standards, on the ISO standards. Also, the proposal is to have harmonized calibration curves, mainly for PCC ring, and also for some laboratories for micronucleus test. Another strategy is to the performance checks by intercomparison exercises, the performance checks of operator qualification by intra-laboratory exercises, performance checks of sample transport integrity, That is, as an example, the SHIP-X1 exercise performed under WHO and IIA project approach. Another way is the performance checks of dose and confidence limits estimation. That is a current desk exercise that is running in the network. The performance checks of result report generation. That is also a current desk exercise. Our laboratory in Argentina is the Biological Dosimetry Laboratory that is accredited under ISO 17025 and the ISO, the specific ISO standard for dye-centric analysis since 2010. And Cuba Laboratory, the Biological Dosimetry, has implemented the standards, and our laboratory in Argentina is the region's laboratory that is registered under IIA REPAN systems since 2008. According to the statistical analysis of the results of the comparison exercise within the network, we have some acceptance criteria of the estimated absorbed dose that is based mainly on the analysis by robust methods. Algorithm A is applied to obtain the robust mean of the results reported by the participants and the robust standard deviation. We also take into account the standard uncertainty, the assigned value. The other important statistician is the performance. To see the performance of the laboratories is the CETA score. In the case that the standard, this condition of the standard uncertainty of the assigned value is not met, then we have to apply the CETA prima score. As an example, if this uncertainty is not negligible, in the case of when an irradiation is carried out under a condition of simulation of a real scenario, just as industrial gammography accident, and not in a laboratory condition where it's a calibrated source against secondary standards and control conditions of irradiation. So this uncertainty should be considered in the analysis. Another situation is an important value parameter to establish the performance is to give each laboratory an analysis, a report, an individual report. These two statisticians, the U score and EN score, unlike the CETA score, take into account the uncertainty of the absorbed dose reported by each laboratory. This condition can lead to a laboratory which was satisfactory by CETA score. It is not in this individualized evaluation. So we consider that it's important to give to the laboratory this results, this return. So another aspect that we include in our quality assurance activities of the network is to some improvements in the report. We include in the report to the medical doctors the decision rule and the risk analysis. The decision rule adopted is for the estimation of the absorbed dose. That is a safety zone equal to the expanded uncertainty that is chosen. This is 95% confidence interval. It is the interval that covers the true dose 95% of the time. And it is built using the methodology of two combined coverage factors, the Poisson confidence interval for the frequency of aberrations and the regression factor R, which is the confidence limit of 95% of the chi-square distribution with 3 degrees of freedom for a linear quadratic calibration curve. So this double coverage interval is conservative. It is, and the risk analysis under the specified conditions implies that the reported dose is considered to be compliant with a probability of conformity of at least 95% and a risk of probability of non-conformity less than 5%. So some aspects that also are integrated to the network is the BioDoseNet image repository. The new laboratories that join the activities of the core laboratories, there are 7 core laboratories and 6 new laboratories from all the Latin American region. So some of the new laboratories were experienced in clinical cytogenetic, but had no previous experience with the dosimetric assay. And various of them have problems in obtaining access to suitable radiation sources and control conditions to construct their own calibration curves, so that they use the BioDoseNet image repository as a dosimetric training tool. So it was, as you know, the BioDoseNet repository was founded by the WHO as a global network of biodosimetry laboratories. And it has this repository is an image repository that has a data bank of more than 25,000 electronically captured images of metaphases for dosimetric assay. It is established on behalf of the WHO by the BFS in Germany and is hosted in the servers of BFS. So it is an interesting tool for training purposes.
Less than 1 minute.
Yeah, okay. So I would like to show some actions that are related with the retrospective dosimetry and the comparison exercise of biological dosimetry with a multiparametric exercise in a simulated scenario of accidental exposure in industrial gammography. This is a total of 37 laboratories or services from 15 countries participated, of which 20 correspond to personal dosimetry services, 9 to biological dosimetry, and 8 to computational dosimetry groups. That is multiparametric evaluation through biological and physical and computational dosimetry. In this case, this is two conditions of exposure, homogeneous and partial body. And then I would also like to show a comparison for 1 point of dose of the biological dosimetry with physical dosimetry results for the homogeneous exposure, showing a close correlation between biological dosimetry results and the physical LTD results of the different laboratories. So I would like to say that there is a network, the LBDNet, it is well connected with international networks such as the results in the RENEV, the participation with the RENEV network. And also, well, I would like to say as a conclusion that proficiency tests are essential tools for the quality assurance of the laboratories, as they constitute an objective evaluation of its performance from both human and technical point of view. So according to the gaps, or what we call future challenges of the biodosimetry role, we think that is important. The strengthening of medical response in emergency linked to biodosimetry as a tool to guide medical treatment, and also to include biodosimetry techniques applied to clinical purposes to support treatment decision in patients. And according to the retrospective dosimetry long-term health risk studies following radiation exposure for the purpose of epidemiology, and the development of biomarkers that also to support medical treatment by the knowledge of bone marrow status and gastrointestinal status. Evaluation of individual radiosensitivity is also considered an important approach. Many thanks.
Thank you, Marina. I think we'll just move right on to the next talk for in the sense of keeping to time. Our next speaker is Dmitry Bazika from the Research Council of Radiation Medicine in Kiev in Ukraine. Is he with us?
Hello. I try to.
Can you share your screen?
Yes.
Okay, we can see that. That's Can you put it in presentation mode?
Sorry. Oh, okay.
Perfect.
So
Okay,
I
great.
will speak about the markers of a late period after radiation exposure in acute radiation syndrome survivors. First of all, about the numbers. These are people who were exposed acutely after the Chernobyl accident and got the acute radiation syndrome. We perform the follow-up of these people. So now the starting point was 190 acute radiation syndrome confirmed and not confirmed. Now we have information only about 73 of them. 65 deaths, cardiovascular is the first place, 25, cancers and leukemia 23, others are lesser. So what we have started? We have done cytogenetics, FISH, HLA typing, T cell receptor variant cells, telomerulans, HAMA H2X, the late period. And now we also perform gene expression in those people who are alive. Now speaking about the acute radiation patients, cytogenetics. These are cytogenetic doses. Interesting is that in acute radiation syndrome of first grade and second grade, the doses, mean doses are almost the same, while in non-confirmed acute radiation syndrome and the third stage of acute radiation syndrome doses differ. This, we can say that we have only partly correlation with physical doses. So the recovery period was characterized by the changes of cellular immunity and occurred mainly in the younger age. The wavy oscillations of expression on surface antigens related to helper-inducing mutagen response, increased expression of pan-B antigens were registered. So we have also studied individual radiosensitivity, and correlation were found between the acute radiation injury and certain HLA phenotypes. I can say that this study was followed by the study in Japan and not confirmed. Also, the changes of recovery period immunologic markers show the highest changes in acute radiation grade 2 and 3. This is the T cell receptor variant lymphocyte cells. We started in the 90s. So when these figures were higher, the mean figures were higher, then the number of T cell variant lymphocytes decreased. Now we show the changes of T cell receptor in 5, 6 to 10 years and 10 to 12 years after the accident. So the correlations are decreasing. These are figures of gamma H2X in lymphocyte acute radiation syndrome survivors. What is interesting that in acute radiation syndrome survivors, the figures are much higher and significantly higher than in control. We regard this as a secondary origin correlated and connected to the secondary pathology changes of the late period after exposure. This study was done by flow cytometry, investigation of gamma H2 storm. This is relative telomere length. Here, two types of response are typical. First of all, in acute radiation syndrome, length of telomere is shorter than in control, but higher than in cleanup workers and staff of the Chernobyl NPP, which works now on the NPP. So we regard it as a change in the dependency. The first year, the dependency, at lower doses, dependency is of decreasing the relative telomere length, and high doses, an increase is detected. Also, the cyclin D1 expression was shown and was increasing. Acute radiation syndrome is the right column. You can see the significant changes in doses over 1 gray. I can say this cyclin D1 changes are also typical for oncohematology pathology, also especially lymphomas. Now we also perform gene expression studies. This is a number of genes that we have studied in acute radiation syndrome survivors. We have shown some dependencies. First of all, dependency between TPP53 and serpin F9, MCFL1, BCL2, and also this is serpin F9. So what can be concluded here, that there is an increase in expression of genes positively connected with the apoptosis, while genes of anti-apoptotic origins are decreased. So the summary of our studies is that certain parameters could serve as biomarkers of exposure at doses below 100 millisievert, and an increase in counts of dissent, spare fragments, and TCR variant cells is accompanied by immune phenotype changes. Increase in expression of H2 histone lymphocytes was revealed comparing with cleanup workers, and gene expression also are the subject of interest in future studies. Thank you for your attention.
Thank you very much. That was a very interesting talk. We are right on time at 9 o'clock. So I'd just like to do a quick summary of this session. I'd just like to thank all the speakers from the session. It was very interesting talks, which covered the realm of the international biological dosimetry networking, focus on one of our very successful networks, the Latin American Biological Network, with some key pointers on statistical methods and quality assurance. And then it also included some information about the type of exercises that could be generated by these members of the network. The RENAM exercise was a fabulous exercise conducted. And then we also covered a few techniques, some new approaches on DNA double-strand break analysis, a very nice review of methodologies for DNA double-strand analysis, and then some fascinating data about looking at biological markers long after exposure. So thank you very much. It was a fabulous, fabulous session. I'll hand the floor back to Jeanette.
Thank you very much, Ruth. Excellent sharing, both of you, Marina and Ruth, and kudos for keeping on time. So we have some questions in the chat session, and specifically one from Liz Ainsbury. And Liz, hello to you, and we don't mean to ignore your question, but we really have to stick to the schedule and move on. And this question I will ask the chairs to answer in the chat. So the next session is session 7, the last one, and it is focusing on public health aspects of radiological emergencies. And for this session, we asked Adila Salami Alfi from US CDC to chair this session. She's a senior service fellow at the Radiation Studies National Center for Environmental Health Centers for Disease Control and Prevention. They used to be our collaborating center, and recently, 2-3 years ago, the collaborating center status lapsed for some technical reasons, because PAHO is maintaining this center as our regional office for Latin America and South America, Pan-American Health Organization. Somehow there was some glitch in the system, let's say, and the status lapsed. So we are actually now in the process of redesignating CDC as a collaborating center. Adela, the floor is yours. Thank you.
Thank you, Janet, and thank you for the opportunity to participate in this meeting today. I was wondering if Professor Richard Amlott has joined the call. Oh, excellent.
I have, yes, hello.
Okay, I'll introduce you. And he's the head of behavioral sciences at the Public Health England. And I will give you a 1-minute warning. We have 10 minutes, so let's go for it.
Fantastic. I'm going to try and share my screen in the first instance so that you can see my slides. If you could tell me that you could see them, that would be great.
We can. Could you just put him on presentation mode?
Yes, I will. Yeah.
Thank you.
How's that?
Perfect.
Good. Okay, so I will do my very best to keep to time with this. So I apologize. There's quite a lot of information on my slides. I've put it there so that you have some links and resources that you should go to. We'll share the slides afterwards to everybody who's attended. So hello, everybody. I lead a behavioral science and insights unit currently based within Public Health England. And we are very heavily involved in the COVID response, but outside of COVID, we provide a behavioral science function for Public Health England's all hazards health protection work. So I thought I would start by highlighting the fact that behavioral science, I don't think, has been as prominent in a major public health emergency response as it has been over the last year in the COVID response. And it's been a very interesting time, and particularly earlier in the pandemic, there was a lot of discussion and debate over the role of behavioral and social science, with some critics, some debate over what behavioral science we should be using. And in particular, this debate rather highlighted the fact that there are some limitations to some of the common behavioral insights and nudge-based approaches to changing health-related behavior when you consider it in the context of a major public health emergency. In order to draw on the best evidence that we have, in the UK, we have the Scientific Advisory Group for Emergencies, and they very quickly set up a behavioral science subgroup, which we're part of, which is a very diverse multidisciplinary group that is supporting the pandemic response. So in terms of what we know about public behavior in major incidents and emergencies of all types, I mean, this is obviously something that's been studied for decades and decades. And whilst the behavioral insights and nudge approaches tend to take a rather negative view on human behavior, where it suggests that, you know, we're not very good at paying our taxes, we're not very good at eating healthily and exercising, and we need to be nudged and sometimes shoved into doing the right thing. What we find, broadly speaking, in emergency situations is that they bring out the best in people. And so there are a lot of myths, and I think Hollywood has an awful lot to answer for in this area, that the public might be panic prone, that we might see a breakdown in social order. But generally speaking, and as has been played out, certainly in the UK and I know across the world, that the most common responses that we've seen have been pro-social. We see communities and individuals supporting and helping each other. We've seen very high levels of compliance, certainly in the UK, to the restrictions that have been put in place. And where we have seen issues, these have very much been a factor of the minority, not the majority response. And incredibly, this far into the pandemic, we still see very high levels of compliance, and we're currently in a state of national lockdown. So when we look at and we prepare for emergencies of all types, we might see and consider things, and here I've got a couple of images. One represents empty shelves following panic buying. The other are people outside in a park in a national lockdown. We need to sort of think about what we're actually seeing. So are we seeing panic buying, or are we seeing a supply chain that is susceptible to small albeit widespread changes in shopping behavior? And if we have told people to prepare to self-isolate for 2 weeks at a time, if people are just buying 2 or 3 of something that they would normally buy once, is that more likely to be the explanation for what we're seeing? And if it is, there are things that we can absolutely do about it. Okay, so our role has been to challenge some of these myths, and this I'm signposting you to this because it's a really excellent commentary from some of our collaborators that highlights that challenge, particularly in the context of a very widely used term, pandemic fatigue. And so pandemic fatigue, I think, is the new panic for those of us who have been working in this area in emergency response, in that whilst people have been using it as a label to apply to a range of behaviors that appear to be happening, really, when we look under the surface, we actually use data-informed consideration of what's actually happening. We see that fatigue is actually and a gradual reduction in adherence to protective behaviors is not common. And in fact, often the opposite is the case. It's just that we find that people tend to psychologize, that is, that they amplify anecdotes. So if you see one person wearing their mask incorrectly, you remember them, but you don't remember 30 people who were all wearing their mask correctly that you passed by on the street. And what we should be doing is using psychology. We should be using data and evidence to inform our understanding of how behavior is or isn't changing. One of the authors of this piece, Stephen Riker, really nicely summed it up, because he said what we need to be doing more of is dramatically telling stories of mundane adherence. So we hear often very loudly about poor behavior and breaches of rules and restrictions, but we rarely hear from the vast majority of people who are making considerable sacrifices in the response. So I'm just going to quickly say a little bit about more of our work here. So right from the beginning of the pandemic, we've been working very hard to try and synthesize a lot of the knowledge and evidence that we have to inform the response. Some of that has become very specific. We do behavioral analyses on the kind of protective behaviors that excuse me, we want people to follow. And this can broadly be summed up as saying that we need to find ways to make protective behaviors easier by improving people's capability to perform those behaviors, the opportunities that they have to perform protective behaviors. And then we also need to change their motivation, and that might be about providing information to increase people's perception of the risks, so that they're more likely to follow our advice. And where there are problematic behaviors or behaviors that put people at risk, we need to be providing information to persuade people. We need to provide them with more support. We can incentivize certain behaviors where necessary or create disincentives. And ultimately, as a final step, we can involve regulation and enforcement-based approaches, but those shouldn't necessarily be where we start. So this is just a slide to say a little bit about some of the work that we've been doing. We've been getting involved both at a local and regional as well as a national level, and our unit exists to support teams across government to apply behavioural and social science to the activities that they're undertaking. So let's jump across very quickly to vaccination uptake. So in the UK, we've had a very successful rollout of the vaccination program, and we're also very lucky in that we have a very vaccine confident population as a starting point. And so you can see on this tracker that's asking the question, if COVID-19 vaccine were made available, I would definitely get it. And what we see is about 70% of people in the UK are saying that they would have the vaccine, and that's only been increasing as the vaccine's rolled out. So again, that speaks to the fact that vaccine hesitancy, broadly speaking, is not something that we've had a challenge with in the UK. However, we do know that there are subgroups of our population who are more vaccine hesitant. And one of the things we've been working to do is to try and identify ways and evidence and insights that can support that. And I'm just signposting you here to some really useful resources on this. And this is another paper which is looking at how behaviors might change once people have had a vaccine. And again, we've been communicating to try and address that in a behaviorally informed way to make sure that people don't take their foot off the accelerator once they've had at least one dose of the vaccine. A lot of our work as behavioral and social scientists in the response has been about synthesizing this. And so we've written a whole range of briefing notes. And I won't go through these in any detail because I'm conscious that I'd like to, in the time that I have available, get to the barriers and gaps. I wanted to show you this one in particular because it's an intervention, a digital intervention for reducing household transmission, which was adapted from a version that was created prior to the pandemic to very quickly focus on COVID. Uses a range of behavior change techniques and represents something that was developed as we prepared for emergencies that could be used in the context of the pandemic. So let's revisit my first slide. So we know that the public and professional communities are some of the most important assets we have in large-scale public health incidents. Now, for those of us who work in the preparedness field, we know that that is the case, but often we do have to convince the decision makers that the public are not the problem. They are an absolute key part of the solution. Now, in radiological emergencies, which are involving dread risks where public knowledge might be low, anxiety might be higher, what we do know is that people will be acting in adaptive and pro-social ways to protect themselves, their families, and their communities. So how do we best communicate and intervene to influence that positive behavior for the better? And I think that is a gap that we continually need to address. My next point here is around mobilizing volunteers. We've seen some fantastic programs of engagement, but how do we mobilize volunteers in support of the response? Because volunteers will come forward anyway. And if we're not part of the efforts to coordinate those volunteers, there's the potential that they could clash with what we're trying to do. And so we need more focus on mobilizing the population. And then how do we test and evaluate the initiatives that we put in place to be sure that they will work? in support. And I think often the public and third sector groups are a missing syndicate in the emergency preparedness exercises that we run. And we need to bring the public and our wider communities closer into the preparedness community ahead of the next major incident. My next point is from a behavioral scientist, so you would probably expect that I would highlight the fact that we need to use behavioral science and insights and evidence to support how we design our interventions and our communications for protective behaviors. And I think that applies in incidents and emergencies of all kinds. And there's an awful lot that we can do in order to prepare ahead of time. So just two more from me. I think we spend a fair bit of time and have done over the last couple of months changing people's minds and bringing them up to speed on our knowledge and understanding about human behavior in emergency situations of all types. And so how can we upskill our colleagues who have expertise and specialism in a whole variety of different areas, but may not be aware of some of the kind of key lessons from the behavioral and social sciences. And one of the ways of doing that, but certainly not the only way, there are various things that we can do in order to train and upskill our colleagues. But one of the ways of doing that is to embed behavioral and social scientists in our organizations and put them close to our responding teams so that they can make a contribution dynamically and in real time and in ways that their colleagues can actually use. And then finally, and probably the most important point in this list, is how do we most effectively address health inequalities, given that the pandemic for us has shone a light on something that, again, if you have worked in this area for some time, that you already knew, which is that when a major incident or disaster strikes, it is those groups that are most disadvantaged that will be most badly affected. So what can we do to build resilience and reduce health inequalities as we prepare for emergencies, and in ways that will actually result in measurable improvements in outcomes within the response? So I haven't heard a 1-minute warning yet, but I'm worried that I'm running over time. I think you might be on mute. Hello?
That must be because everybody is fussing.
Oh, I did, but probably I was muted. I'm sorry. I gave you a 1 minute a few minutes ago.
I thought that was the case.
I apologize. You didn't hear me. I had double muted myself. Sorry.
No worries. So the only 2 slides that I had left here was to highlight something that, if you're interested, you're welcome to sign up to receive, which is that for about 42 weeks now, we've been publishing a weekly literature report, which is all about behavioral science as applied to COVID. Now, again, I've talked a lot about COVID, but what I hope you'll hear is that a lot of these lessons are very applicable to the radiological emergency context. And what we're intending to do is that once COVID hopefully has come off the top of the list of things that we're dealing with, would be to refocus some of these outputs that we're producing, including a database of these reports for you to search on an all hazards focus. But that's me. Thank you very much.
Thank you. And I'm sorry you didn't hear the warning. I hope you can hear me now.
I can, yes. Yeah.
Oh, great presentation. I wish we had more time. There's so many lessons. Thank you so much. And I think now it's my turn. So Jeanette already introduced me. So, and I'll set the timer for myself. So I make sure, and can you see my slides?
Not yet.
Not yet. Okay.
Beautiful orchids in the background.
I'm sorry.
At the trying session, you did it perfectly fine.
Okay, how about now?
Now it's good. Yeah, we see you.
Okay, thank you. Okay, Well, thanks again, Shanat, for the opportunity to speak to this wonderful group. I want to talk to you about our latest initiative. It's an in-house program to develop a radiation-savvy public health workforce. And this is pretty much what I'm going to cover, our CDC Nuclear Radiological Training, Exercise, and Preparedness Program. We call it the TEP program. A little bit why we need a radiation-savvy workforce, some of the elements of that RAD-savvy workforce, and some of the training topics that are available in some CDC resources. In 2016, we established this program, this STEP program, and the idea was to better prepare and respond to a nuclear emergency across the CDC wide community. So in this effort, we have engaged people, epidemiologists, clinicians, data managers, communicators, environmental health specialists, people with at-risk population specialties, et cetera, because we recognize everybody's going to have a role during a radiation response. So we wanted to establish a CDC-wide nuke-RAD response responsibilities and capability, and we established an incident management system structure that's made up of staff that is organized, trained, and ready to respond to a nuke-RAD incident. And our scope includes both preparedness, response, and recovery, and we achieve that through planning, workshops, drills, and exercises. At the same time, we try to identify and remedy gaps, training needs, and challenges. So our program continues to be improved every time we exercise. And we do follow the preparedness cycle. That's the planning, organizing, training, and exercise, and evaluate and improve. So as part of the planning, we have updated our CDC-specific nuclear radiological incident annex. Again, as I mentioned, we have organized and improved our incident management system structure. We started with the structure we had during the Fukushima response, and we have revised it based on our experience with responses to natural events, and most recently with the COVID response. We do a lot of training and exercises, both workshops, tabletop drills, and full-scale exercises. And we continue to, again, evaluate and improve. Our overall goal really is to have a workforce that's better prepared to respond to a nuke-RAD incident. And this chart, I just want to show you the progression. Every year, we define activities that we do every quarter, and it's here lists, some of the workshops, tabletop exercises, and our approach is to follow the crawl, walk, run. When we started, we were just beginning to crawl because it was only a handful of us that were very familiar with radiation response. But as we've moved, we're advanced our knowledge and expertise across the agency, and I'm happy to say we have a lot more RAD-savvy people now than when we started in 2016. Now, why we need a RAD-savvy workforce, and this could be pretty obvious to this group, but we know that a nuke-RAD incident can happen anytime, anywhere, and will likely impact all sectors. This need was identified as a part of the TEP program because we need to support the nuke-RAD response when the availability of radiation subject matters is limited, which is the case in our agency. We are a very small core group of radiation specialists. So we need to make sure that the rest of the community has some awareness and some knowledge on some of the radiation issues and radiation terminology. And this allows our small number of SMEs to focus on more technical or complex questions that will arise during an emergency. By training this workforce, this can act as a force multiplier when we have limited resources. And it also helps the team member understand their roles and responsibility during a nuke-RAD emergency. Many people didn't even realize that they will have a role during a RAD nuke emergency. Unlike a biological response, they need to realize that, again, the whole of community will have a role in responding. And it also helps create a common understanding of the key concepts and terminology, and thus allowing us to streamline the response during real events. Of course, a trained workforce is ready to act when needed. And these are some of the elements of a RAD-savvy workforce. We cover stuff from basic radiation principles, basic radiation preparedness concepts, what the roles and responsibilities are, what resources are available, and we want to make sure they're comfortable conveying basic radiation protection information to their task force members. By doing that, they free up our time again so we can focus on more complex questions that may need to be answered. How we approach developing a radiation savvy workforce? Well, we have defined 3 different levels of rad savvy concept, and I'll show you in a moment. We have level 1, 2, and 3, and that's based on the radiation knowledge and level of expertise. We train across all the CDC programs, and we use a mixed approach. We use in-person, webinar, self-study, and online training materials. We have a lot of information on our website, so we want to make sure we direct our staff members to go and do some of the self-learning. We design and conduct specific task force or team wide tabletop exercises, drills, and we also participate in national full-scale exercises. And we prepare after-action reports, and when we do that, we identify remaining gaps, remaining needs for training, and we try to work on that for our following quarters. So this is in a snapshot, the RAD savvy levels. The RAD level 1 from the bottom up is people that just had some just-in-time training in radiation basics. They're familiar with how to operate in the emergency operations center. Or they might be people that have no radiation response experience, but have been participating in other responses. People that may have some radiation training that go beyond the awareness training, or some experience in radiation preparedness and response will be placed at the level 2. And level 3 will be people like myself, health physicists, or other people that have advanced radiation training, or we have some clinicians that have gone through a lot of the radiation training courses. They're also at the level 3 RAD savvy level. And this is just a training outline. I'm not going to list it. You will have the slides, but this is an example of some of the training we provide. All the information is on our website. I listed the websites. I encourage you to check it out. We have a lot of information. Could you please mute your lines? I hear some background. This is information for professionals, and we target information for clinicians, for public health professionals, for laboratorians. We talk about population monitoring, medical countermeasures. We have some training, education, and tools, and some of those you can get continuing education. And these are some examples of our training resources. We recently published a radiation response briefing manual. This is a short manual that any public health person can read in maybe 2 hours and bring some information to get awareness of what the key questions are going to be, what are the basic concepts. So somebody that has to be deployed that has no radiation experience, is a very quick guide to how to go about it. And that's also available on our website. We talk about radiation basics. We have also myths of radiation, which will follow very nicely with some of the myths from COVID. We realize that people have a lot of misconceptions about a lot of things. Just quickly, our successes and challenges. We have over 250 participants that are continuously engaged in our meetings and exercises. Even with COVID, we still have pretty good participation. We had a cross-agency participation in 2017 in a national level exercise. The task forces that have been stood up have a better understanding of the roles and responsibilities. They continue to be interested, and again, the workforce can attain the 3 levels of preparedness. The sad news is, as you can imagine, with staff turnover, many of them have been unavailable due to the ongoing activation. We're going in 14 months, I think, and their staff workload and competing priorities. But again, the fact that we have a core group that continues to participate is very encouraging. The path forward, we want to continue the basic training. We want to target new staff because of the staff turnover. We are offering and delivering more advanced training topics. We are currently designing an in-depth radiation training course that will be 2 to 3 days, maybe with possibility of providing continuing education credits. And we want to continue engagement with our community of interest by continue to plan and execute these workshops, tabletops, drills, etc. And we want to continue CDC-wide participation in upcoming national level exercises. So just a quick takeaways. Your organization may have the same issues, that you have few radiation experts. This model may help better prepare your organization to respond to a nuclear incident. It's very key to have across-the-board rad-savvy staff, especially those with experience in other emergency responses. Radiation SMEs play a very key role, but to be successful, we really need to engage planners, exercise designers, etc. I cannot stress enough, management support is essential. We've been very lucky to have very good support at very high levels, and that allows us to continue with this program. And it takes more than radiation experts to have a successful response. And just a quick, we don't have really research gaps, but we wanted to summarize that one size does not fit all. We need to assess the current level of training, need to identify specific training needs specifically for subgroups among the staff, need to evaluate staff turnover rate to determine how quickly or how many training sessions we need to do. We need to identify internal and external partners for training, evaluate the best platforms to deliver the training, and identify how best to sustain training. And this is my last slide, and thank you very much for your attention.
Thank you, Adela. Actually, when you say that you need to identify certain things, this in a way it is a research, because how do you identify if you need to do a survey, if you need to evaluate the situation, it is a type of research as well.
Thank you. You're correct, Joanna.
Thank you for the presentation.
Thank you. All right. I would like to introduce Dr. Lee Kuping. Is that how you pronounce it? I hope I pronounced it correctly.
Kuping.
Yes, thank you very much. And she's a researcher at the National Institute for Radiological Protection at CDC China. So go ahead and I'll let you know when you have 1 minute left.
Okay, thank you, Chair. Thank you, Janet. Dear colleagues, it's a great opportunity to introduce National Capacity Building and Training Program in China. As we know, even after Fukushima accident, the application of nuclear power is rapid in the mainland of China. By the end of 2020, there are 15 nuclear reactors in operation and 12 nuclear reactors under construction in the mainland of China. As we know, nuclear and radiation technology is a double-edged sword. Once the severe accident happens, it may cause catastrophic consequences, not only to the physical and mental health of the public, but also to the environment. In order to strengthen the preparation and response capacity to the nuclear emergency, Chinese government established the National Nuclear Accident Emergency Coordination Committee in 1995. Now, the Coordination Committee is composed of 22 ministries and bureaus of the state council and military agencies. By the 2014, the Coordination Committee set up 8 types of professional technical support centers and 3 response training bases and 25 professional response teams. Covers medical response, radiation protection, radiation monitoring, decontamination, and so on. This figure shows among the technical support centers, there are 5 medical centers. My institute is the main center, and Institute of Military Sciences, Second Hospital, Suzhou University, and Institute of Radiation Medicine, and Army University of Medical Sciences are the other 4 sub-centers. Among the 25 response teams, there are 13 medical response teams in different regions, and 2 medical training centers are established in Suzhou University and Academy of Military Sciences. The National Health Committee is one of the members of the Coordination Committee. and responsible for medical preparedness and response for nuclear and radiological emergency. In order to fulfill the mission, National Health Committee promoted the establishment of medical treat bases for nuclear and radiological emergency. The bases are responsible for medical treatment of radiation injuries, radiation monitoring for food and drinking water, dosimetry, and health effect assessment, putting forward the strategies to protect public health, medical follow-up for overexposed cases. By 2020, there are 6 national bases distributed in Beijing, Tianjin, Liaoning, Jilin, Jiangsu, and Guangzhou, and another 19 provincial bases distributed the provinces with nuclear power stations and or other nuclear facilities and border areas. This map shows the distribution of the medical bases. The red spot represents provinces with medical bases, and the black spot represents the provinces with a nuclear power plant or nuclear facilities. Except for the establishment of medical bases, the National Health Committee has established 4 levels of public health response systems, from the national level to the provincial, municipal, and county levels. The health administrative agencies at each level, they will designate the institutes and hospitals who take the task of radiation injury treatment and radiological monitoring and protection related to the public. Furthermore, our institute, as the National Chinese Center for Medical Response to Radiation Emergency, we developed a competitive platform. 33 provinces and cities with nuclear power plants must report their capacity status every year. The survey includes the capacity of radiation monitoring and radiation injury treatment, professional instruments and equipment, professional personnel, training and exercise, stockpiling of drug and other materials. Besides, our center also organizes food and drinking water radiation monitoring in 31 provinces every year. Also organize radionuclide gamma analysis and total alpha and beta measurement and biodosimetry every year, comparison of every year. Above is about the capacity buildings. Now I will briefly introduce the training program. Basically, our institute hold 4 kinds of training courses. In past 10 years, our center has held more than 20 training courses over and about 1,300 staffs from provincial health committees, provincial institutes, and hospitals were trained. The 4 courses are basically health preparedness and response to nuclear and radiological emergencies, medical management of radiation injuries, dose estimation of internal and external exposure, and exercise design training for medical response to radiation emergencies. I will not introduce the detailed content of each class, but I want to mention that from 2019, we added the content on risk communication, mental health, and psychological support in the training courses. Last year, we invited the experts who attended the mental health and psychological support to COVID-19 in Wuhan to give us the courses. Here are some pictures about our training. In 2019, we are honored to invite Dr. Janat to give us a lecture on iodine thyroid blocking guideline and risk communication and mental health management. And we also sometimes organize the courses to students around the nuclear power plant. Oh, this is a training and exercise system we developed for the prevention from the municipal and county level professionals. They do not have the opportunity to attend the national training courses. So we developed an online training and exercise system for them. Exercise is one kind of special training. Every year, we will organize different exercise for the national response teams, from tabletop exercise, specific skill drill, and to full-scale exercise. Before the end, I want to share the good news that my institute was designated as a WHO Collaborative Center for Radiation and Health in 2019. Dr. Maria attended the ceremony, and one of our key jobs is to the medical preparedness and response for radiation emergencies. Regarding to the research gap, I'm doing the management work on medical response to preparedness and response to nuclear and radiation emergencies. I think the key is how to design the plan and the procedures according to the actual situation or scenarios, as much as possible in every step, every site, like stable iodine stockpiling and distribution plan.
1 minute.
And decontamination plan for large populations. As far as stable iodine thyroid blocking, some Chinese experts are concerned about the side effect and contradictions of stable iodine, but it seems little research on them. And also the treatment of patients with high dose and the patient exposed to electron beam is very important. That's all my talk, and thank you very much. Thank Janet for her hard work for the REPAN and this meeting. Thank you for all the outstanding lectures. Thank you.
Thank you very much. Thank you very much. Fantastic presentation, and you stay within your 10 minutes. So I commend you. You're setting a great example, and lots of very, very interesting training. If I may ask Dr. Eugenia Ostromova, I hope I pronounced it correctly, to go ahead and share. Perfect. If you can share your slides, that will be great. And I will give you the 1 minute warning as well. Thank you. Oh, and I'm sorry, she's a researcher in the International Agency for Research in Cancer at WHO. Thank you so much.
Can you see my screen? I put it in the...
I can see it. Yes.
And now it's in the...
Perfect. Perfect.
Okay.
Thank you.
Thank you. Thank you, Madam Chair, for the kind presentation. Yes, I'm a scientist of the Environment and Lifestyle Epidemiology branch, formerly Environment and Radiation section of International Agency for Research on Cancer. And I would like to thank Janat for giving the opportunity to share today our experience regarding long-term epidemiological follow-up in populations exposed to environmental sources of ionizing radiation. Recently, IARC was coordinating 2 EC-supported projects on Chernobyl and Semipalatinsk, as well as leading a project on thyroid monitoring after nuclear accidents, TMNUC, funded by the Ministry of the Environment of Japan. The projects were carried out in close collaboration with international experts from a variety of fields, including radiation epidemiology, radiation dosimetry, pathology, cancer screening, oncology, endocrinology, and mental health. Among the research questions considered in the project, special attention was given to the requirements for sustainable long-term follow-up of populations at risk to ensure a comprehensive evaluation of health consequences after exposure to radioactive fallouts. And the results of the outcomes of these projects are publicly available as the reports. IARC also was a partner on EC-funded project Shamisen, aimed at producing a set of recommendations that would contribute to health surveillance and related communication with affected populations after nuclear accidents. A number of recommendations are on epidemiological surveillance at different phases of a nuclear accident, including the epidemiological surveillance performed in the long-term recovery phase. The following slides will present the synthesis of all the above projects in respect to requisite for setting up long-term studies. The main limitation of previous post-accident health surveillance and epidemiological studies were the difficulty of clearly defining and reaching the affected populations and lack of minimal individual information. The creation of a roster of persons affected by nuclear accident during the emergency phase is a major element for the success of post-accident health surveillance and epidemiology. It serves as the basis to define and trace target populations for long-term follow-up. Inventory and review of existing health monitoring systems with particular emphasis on cancer registers is another key point. Dose assessment is a critical issue in radiation protection of individuals, from workers in charge of responding to the accident to the general populations living within the adjacent areas. Evaluation of doses after a nuclear or radiological accident is crucial for later health surveillance and epidemiology studies. Information on factors that could be associated both with exposure and study health outcome is very important, especially in situations where people were exposed predominantly within low dose range. And the last but not least is availability of biospecimen collections that could be linked with epidemiological data. A creation of common roster of the affected populations allows efficient medical and health follow-up and facilitates long-term epidemiological studies. Based on various criteria, including exposure levels, population groups at higher risk, like pregnant women or small children, also taken into consideration concerns of the affected people, a target study population can be identified from the roster. National Chernobyl registers existing in Ukraine, Belarus, and the Russian Federation serve as an illustration of such a roster used for long-term epidemiological studies, although the follow-up methods and information collected could vary between the countries. Lifespan studies of affected populations and the atomic bomb survivors in Japan represent a golden standard for such a lifetime follow-up, have provided an important opportunity to comprehensively study the consequences of exposure over time, particularly because many important diseases, both cancer and non-cancer, have long latency periods. Health monitoring systems could vary widely from one country to another and even within the same country. Moreover, health monitoring systems cannot always provide data on disease incidence at the local or even regional level, or at a sufficiently precise diagnostic level, for example, disease subtypes. This can be due to lack of validated data, difficulties in producing a harmonized diagnostic definition. In this case, development and use of standard examination and or screening protocols make possible better harmonization and linkage of health outcome data within and between countries. All aspects related to data protection and ethical rules need to be addressed and resolved. The utility of health monitoring system data for the purpose of long-term follow-up is determined by disease registry coverage, exhaustiveness, recorded diseases, and level of diagnostic details. In situation of missing data from disease registries, an opportunity to use surrogate health databases and their reliability for health monitoring and the use of the other health and social service records, for example, health insurance or hospital discharge records, need to be explored. The use of the data from health monitoring system should be done in compliance with data protection and ethical rules, as I already said. In a lack of centralized databases or absence of uniformed approaches for data collection and registration, usage of the data received from the health monitoring system from various regions of the same country and between countries represent a big challenge in linkage between databases. While setting up long-term follow-up, more detailed dose assessment and further precision where possible of doses received in the early and intermediate phases after the nuclear accident are essential to support epidemiological research. While group doses are adequate for epidemiological surveillance using ecological study design, focused at monitoring time trends and comparing incidence rates between groups with different dose levels, analytical epidemiological studies aimed at radiological risk assessment require reliable individual or at least individualized doses and their related uncertainties to be estimated for each study participant. Some key components required for reliable dose assessment are listed on this slide. An important aspect in dose reconstruction is a harmonization of methods and tools used for dose assessment between the affected countries, like in case of the Chernobyl accident, to allow future combined data analysis. As I already said at the beginning of my talk, a collection of information on factors that could confound or modify an association between study health outcome and radiation exposure is very important, but also very challenging. Out of several potential confounders, the special significance nowadays has information on exposures due to medical diagnostic procedures, especially when exposure following nuclear accident was in a low dose range. Collection and preservation of tumor tissues and paired samples of normal tissues or blood is essential to study somatic and germline changes involved in the radiation carcinogenesis. This is particularly important for major radiation events where large numbers of radiation-related tumors occur with known long latency and possible molecular evolution of the tumors over time. Storage of such samples allows the future application of novel modern molecular techniques, which may enable answers to some of the basic questions in carcinogenesis and especially in radiation-induced carcinogenesis. A long-term follow-up is established to provide a comprehensive assessment of the late health consequences and of the use of health and social services after a nuclear accident. To be useful, it should be set up in consultation with affected populations, taking into account the exposure levels. As in case of Chernobyl, the accident affected neighboring countries, and collaboration between countries is essential to ensure complete coverage of exposed population follow-up programs. The maintenance of long-term follow-up, including health monitoring of the affected populations, could be challenged by political, financial, and social limitations. What are the requirements to ensure the long-term follow-up? The construction and maintenance of research infrastructure, such as databases, rosters, collection of biosamples, is essential. And this maintenance also includes qualified staff to conduct the long-term follow-up. It is important to maintain confidentiality and dignity of the study participants through the course of the follow-up all the time. To foster a dialogue between scientists and public health specialists, decision makers, and population representatives about the study findings and concerns of the affected population. And a certain flexibility should be envisaged to adopt or modify the follow-up protocol when needed based on the follow-up experience.
1 minute.
Thank you. So this is my last slide to summarize the existing gaps in challenging setting up the long-term follow-up. So of course, the biggest, the highest importance has lack of early phase data, early phase after the nuclear accident. The gap could be due to the absence of initial data on disease, baseline prevalence, or incidence. The challenge represents, as I already said, variation in disease diagnostic criteria, registration, and reporting practices, even within one country and also between countries. There is an important point about the need for exposure assessment, harmonization, and standardization to assure the correct risk assessment. And another important point is that beside the few examples like Chernobyl Tissue Bank and NCI supported projects, the collection of biosamples previously been done ad hoc and rarely linked to epidemiological studies. This is my vision and my points summarized as the gap and the challenges to setting up a long-term follow-up. And thank you for your attention.
Thank you very much, Eugenia. Very, very interesting presentation. And there's a lot of challenges, but you gave us a lot of very good ideas how to go about collecting some of that data, especially if we know in advance, we can plan to how we're going to collect that data. Thank you so much. And now I'd like to invite our last speaker for the session, Dr. Segmet, and I hope I pronounced that correctly. Is a radiation oncologist from the National Cancer Center of Mongolia. Perfect, I see your slides. And if you could just put them in presentation mode, we'll be ready. And again, I will give you the 1 minute warning. Thank you so much. You can go ahead. I can't hear anything. Do you have your microphone unmuted?
Sorry, can you hear me?
I can hear you perfect now. Thank you.
Thank you very much for your
Thank you.
nice introduction. My name is Orhan Çelikçimit. I am head of Radiation Safety Committee of the National Cancer Center. It is for me the first time participating in REMPAN coordination meeting, so I'm very pleased to give such an opportunity to share a radiation emergency system in Mongolia with you. Let's start first part of my presentation. Some of you who are not familiar with my country, Mongolia is located between Russia and China with a 3.3 population. And first X-rays were used in Mongolia in 1934, and in health sector, Nuclear Energy Commission was established in 1962, and Mongolia joined WHO and IAEA in 1962 and 73. There are the several laws in action, you can see here, and main legal documents is regulation on the intersectoral information exchange and prompt responses in the event and potential disaster. It was approved by the Deputy Prime Minister in 2017. A National Action Plan for the Protection of the Radiological Accidents was approved by Government of the Mongolia on December 23rd, 2020. It contains backgrounds and warning and information of the radiation accidents and prevention and preparedness plan, responses plan, evacuations, etc. You can see here is coordination system of the cooperation between organizations working in a case of radiation accidents. The General Agency for Specialist Inspections is assigned as a leading organization in a case of radiation emergencies. National Emergency and Management Agency, Ministry of Health, Ministry of Transportations, and other organizations, including General Agency for Police and National Center for the Public Health, saying that the cooperation organizations and Nuclear Energy Commissions is assigned by a supportive organization. Let's move to the next topic. Nowadays, nuclear technologies is applied in various areas, including health, agriculture, environment, etc. The main reasons to establish a system for radiation emergency in medicine in Mongolia is as follows. Nowadays, applications of nuclear technologies in different areas have been largely expanded. Modern technologies are newly introduced, particularly in medical sector, and these significant challenges are posed in the quality assurances of the advanced nuclear technologies, as well as radiation safety and protection issues. In Mongolia, there is a possibility of the radiation accident could be of the third and fourth, fifth categories of accidents classified the IAEA. Also, there is a lack of specialists in radiation disaster medicine. If any radiation accident happens, our country does not have a radiation emergency medical team and system for radiation emergency medicine. Therefore, it is crucial to develop system for radiation emergency medicine and prepare human resources in field of radiation emergency medicine. Let's move to the last part. Significant challenges are posed quality assurances and radiation safety and protection issues. Lack of the public understanding and awareness about radiation accidents because there was no major radiation accident in Mongolia. Also, lack of the specialists in radiation disaster medicine, as I mentioned previously, and lack of the education training program on radiation emergency medicine, and lack of general understanding and implementation of the safety culture in nuclear technology users and facilities. In addition, lack of the radiation and contamination detection instrumentations instrumentation and professional dosimeters. Due to none of the system for radiation emergency medicine, it is not clearly determined the structure of the medical response organization in a radiation emergency on the National Action Plan for Protection the Nuclear and Radiological Accidents. In general, understanding of stakeholders about radiation emergency medicine is lack. Therefore, the National Poisoning Emergency Center, which is assigned to provide radiation emergency medical care, but that center doesn't have any radiation emergency medical response team and specialists in addition to detection equipment. And our messages on urgent demands to establish a system for radiation emergency medicine have been delivered to the government and decision makers. However, the decision makers and officials at the ministries or government are unstable at their work position because of the political reasons. We have the opportunity. The Radiation Safety Committee of the National Cancer Center of Mongolia is playing a vital role to establish a system for radiation emergency medicine. We believe that our cancer center can prepare a radiation emergency medical assistant team. The reason why we use the high energy, high active radiation doses for the cancer treatment. Therefore, there is a radiation oncologist who have experience to deal acute and chronic radiation syndromes. In addition, we have the medical physicist, and therefore we could respond to accidents as an advanced radiation emergency medical support center. National Cancer Center of Mongolia have submitted project proposal that to develop a radiation emergency medical support center to the government of Mongolia, also the government of India and Rosatom, etc. It haven't yet accepted and supported. However, we are still keep going. The step toward to establishment of the system for radiation emergency medicine in Mongolia should include establish of the 27 national and local radiation emergency response capacity at the National Cancer Center, and prepare a specialist and other human resources in the field of radiation emergency medicine, and also introduce cytogenetic biodosimetry laboratory with capacity to perform decentric and other chromosomal analysis for radiation biodosimetry purposes. And educational training on radiation disaster medicine is crucial to provide to continue medical education. It is field of expertise through regularly scheduled courses for medical professionals and medical students, and also first responders and publics are important. We have organized several workshops on radiation protection and medical responses to radiation accidents. First, in 2019, National Cancer Center as Radiation Safety Committee initiated that workshop, and participated medical professionals and radiation workers from the Ulaanbaatar and also the provinces. That workshop contains the conferences also drilled. You can see here some photo. We extended this workshop in 2019, and that workshop was supported by Prime Minister and also WHO and the National Cancer Center with the regulatory bodies, including Executive Office of Nuclear Energy Commission and the General Agency for Specialized Agency. Participants were 128 medical professionals and radiation protection officers nationwide, and we invited international experts from Japan and Australia. The workshop contains a conference, drill, and discussion part. In conclusion, it is crucial to establish a system for radiation emergency medicine and also to establish a radiation emergency medical center at a tertiary level hospital with the human and equipment capacities for radiation emergency. And it is crucial to prepare a radiation emergency medical response team and radiation survey instrument and supplies. Also, the regular training on radiation emergency preparedness and responses are needed for healthcare providers in order to properly respond of the potential radiological accidents. Supports and aids from international organizations, institutes, universities, and private companies are essential to implement projects on establishing system for radiation emergency medicine, and including experts missions and financial assistance, organizing training and workshops, procuring radiation survey instruments. Thank you very much for your kind attention.
Adela, you are muted.
Oh, okay. Sorry. I said thank you so much for a wonderful presentation. And I was saying that you laid out a lot of challenges, but you gave us a very good path how you're going about knocking down some of those challenges and getting a nice radiation and medicine program. So thank you so much. I think that's the last of our speakers, Janet. And I've been doing a little bit of summary at the end of each talk. I don't know if you still want me to do some or.
Yes, by all means, if you could just do it very short, within a couple of minutes.
Certainly. We had, of course, we kicked it off with a very interesting presentation on some of the COVID-19 lessons learned for radiation emergency preparedness. And I think in our field, we all seen a lot of parallels, but it was a very good conversation about the psychological myths and assumption in the role that behavioral science can play in helping us with the messaging. I covered our training and exercise program for radiological emergency preparedness and the concept of radiation savvy workforce. Dr. Li Kuping covered the National Capacity Building and Training Program in China, and she talked about a lot of programs and a lot of training that they have developed over the last few years. Dr. Ostromova talked about the criteria and requirements for setting up a long-term follow-up, talked about her experience with some of the work with some of the Chernobyl and recommendations and procedures to move forward in setting up and overcoming some of the challenges. And Dr. Sekmet talked about the challenges in Mongolia for establishing a system for radiation emergency medicine and their path forward to advance that going forward. So I think that's pretty much it for our session. Okay. I'll turn it over to you, Janet.
Thank you. Thank you so much, Adela. Very nice summary. Okay, so we have some 20 minutes remaining to for our closing session. I really appreciate everyone who connected and who is staying online. We are now down to 109 participants. Earlier, there were about 130 people connected. Many thanks to all speakers of today's session. And with that, I'm happy to start the closing session. So I want to thank Dr. Rita Schneider, who is behind the scene, and she is compiling everyone's summaries, and she prepared us a very nice presentation. I wanted her to show it, but she preferred that all chairs of sessions. I hope all of you are connected. Let me share my screen. I will be showing Rita's presentation, and I will invite each chair, if you are available, to quickly go through the research agenda. So what we did actually, we asked each chair of the session to compile First of all, we asked all speakers to prepare a list of research gaps. And most of you have included in your presentation a list of research gaps and needs. So we asked each chair of the session to compile these and come up with a list of bullet points for each topic. So very first session was new members introduction. So obviously we skipped that session. The second session was chaired by Marcus Greshnik. Marcus, are you online?
I am.
Excellent. He is awake at 1 a.m. in Australia, really a hero. So we don't need to read all the names and titles. People can see that. I can go to the next slide and we just go directly to the gaps. Would you like to pronounce them?
Yes. Well, I guess one of the things about this particular session was that the different presentations were some were from a country's point of view and some were from international organization point of view. So I've tried to capture all of the things discussed in this slide. So looking at the contributions to the international and national emergency arrangements with the examples from the IAEA and the NEA, OECD, as I said, the international organizations. Some of the emphasis, well, the importance of cross-sector coordination, maintaining national capabilities and human resources and technical expertise were all mentioned throughout each of the presentations. There was certainly, well, the way I saw that across all of those presentations, there was an emphasis on capacity building and continual improvement, particularly for the medical response to a nuclear or radiological emergency. The value of exercising was identified and as a way of identifying weaknesses and gaps. Accidents and incidents, both minor and major, were discussed, and the responses provided and lessons learned were discussed to different extents. And also there were some things to keep an eye out for. The upcoming national improvements and international advisory documents were discussed. So that slide sort of captures the session, hopefully. Thank you.
Thank you, Marcus. I want also to mention, to remind network members that we have these biennial newsletters, and we always ask you to send us your news, your publications, and some great publications that came out recently. For example, Australia's new publication, Your National Plan, and other things. So it is really good if you could keep this good work and continue sharing information with us and sending us links to your new publications and activities. We will include them in the newsletters. Moving on to the session 3, chair was Dr. Matthias Port. Here's a list of presenters and topics. Matthias, are you there?
Yes, I'm there. Can I get the screen?
Yes, here's your session.
Okay.
With the research gaps, yes.
Go ahead. Wonderful. Yes, yeah, we had a wonderful session about radiation injuries, and we started with the acute management, the acute radiation syndrome, and started with treatment. There was a session from Leif Steenke. We moved on to stem cell therapy given by Radia Tamara. So local irradiation syndrome. Then I gave a talk about diagnostics, but especially not to deal with dose reconstruction, but to deal with clinical guidance. We got a wonderful talk from Carol Iddens about identifying of sentinel science and education. And we closed with a talk from Andrea Di Carlo on medical countermeasures and all the activities at NIH and an impressive 600 products they have under review. There are still some research gaps we have to address. And I think that's, is it the next slide? I'm not sure.
No.
No. Okay, so they go back. So we have research gaps left. First, for ARS, we think we need definitely a new update on the consensus, but we also need a consensus on internal contamination and maybe also on diagnostics. We furthermore have to increase our research on stem cell therapy, including mesenchymal stem cells of different origins, cell-free systems, allogenic administration, and standardized production. That's all for local injury in stem cells. For diagnostics, we have to guide the clinical decisions, and we have to include signs and symptoms, clinical dosimetry, and biological dosimetry, and also to integrate all other data available, and we have to upscale for possible large accidents. With the Sentinel science and educating the healthcare communities, it brings us back to bring all this to the clinics and to the people doing the job, and to identify how to recognize radiation accidents, especially small accidents, which might be difficult to access at the beginning. And this wonderful countermeasure program of the NIH, of the National Institute of Health, it's an excellent example how we have to proceed with our research, and that we not only have to care for countermeasures, but also for decooperation agents, and that we need somehow a discussion on biodosimetry devices and the question, how do they have to be cleared? So that's for the incidents, and I thank all the talks, the speakers from Karolinska, Oak Ridge Institute, NIH, IRSN, for this wonderful section. Thanks.
Thank you, Matthias. Of course, when we compile the meeting report, we will be taking more detail from each presentation, and this is just a snapshot, short version. Thank you. Move on to the session 4 on internal contamination, which was chaired by Chunsheng Li. We had only 4 presentations in this session. Here's the list of presenters and topics. And the research priorities were structured as follow. Chunsheng, are you there?
Yes, Jonathan, I'm here. As shown on this slide, for this station, we have identified a number of gaps we need to do research to fill. The first one being screening throughput at early dose. So we know that in emergency, especially when many people are involved, affected, if we can provide them very early information on the dose and the risk they have, that will be very helpful, especially when we have better information technologies. We have new challenges, actually. So we need to work on this one. Monitoring and the dose assessment part, we have been working to develop a faster, more sensitive method for many years, but still we need a new method for some it's hard to measure radionuclides, and more important, we need to increase throughput for an individual lab, and we also need to increase search capacity for our response. So we think we need to work on the lab networks, in the national, regional, or international lab networks. Medical countermeasures, the research part, we need to develop or improve some available, develop new or improve current available decooperation agents. We know that in US, they are developing HOPO and a very good one. But for other radionuclides, especially the new ones used in medicine, we don't have a method yet. We need to develop this. And we also need to think about how to make the currently available countermeasures more effective, so we can save the dose. Means that we use the limited dose in our stockpile to treat more people in emergency. This is very important. One more thing on medical management is the guidelines. We have guidelines, and over the years we have new clinical evidence. We need to review them and to develop a practical guidelines on these parts. The last bullet, we have developed the capacities, capabilities. We need to make sure they are sustainable. They can be used anytime. We don't know emergency when we're going to have this kind of emergency. We need to think about this one. Thank you.
Thank you very much. Moving on to the next session. Oh, I'm sorry, there was another slide, but this is the more detailed, the same information.
That's fine. That's fine.
We will include it in the report.
Yeah.
Session 5 was chaired by Professor Christoph Reiners. It was on radiation and thyroid, and we also had 4 presentations. Here are the names of presenters and titles of the presentations. It was focusing most on thyroid-related areas. Professor Reiners is not unfortunately available, and I wonder if Rita, would you like to cover this, or I can do it myself? Rita, I can't hear you. So this, yeah.
Let's do it, John.
You will do it?
No, you do it.
Okay.
I'm not prepared.
All right, me too. I'm just going to read it from the slide. So Professor Reiners identified the following research gaps from those presentations. First is on medical approval of KI tablets for thyroid blocking, role of Wolff-Chaikoff effect for thyroid blocking in healthy people and patients with thyroid diseases, effectivity and safety of ITB in people over 40 years of age. More data is needed. I agree with that, because it's still being discussed and debated whether it should be done or not. Thyroid dose measurements in people exposed to radioiodine. Strategy: when, where, who, and how should be measured. Detailed protocols and criteria are needed indeed. Use of dedicated instruments to be used in the field. Broad use of ICRP 153 model for thyroid dose estimation, including multiple mechanisms of thyroid regulation, have to be better understood. Age and iodine diet dependencies have to be studied, and I would add the role of iodine deficiency. ITB for prevention for hypothyroidism, including mechanisms for development of hypothyroidism, not well studied. Different radiation sensitivity for internal and external exposures is not yet clear. Search for dose threshold considering age, exposure, and stages of hypothyroidism could be interesting, and safety of prolonged ITB use in workers. So these are quite a nice list of research gaps where one could consider launching new studies. Session 6 was co-chaired by Ruth Wilkins and Marina Digiorgio, radiobiology and biodosimetry. The list of 5 presenters and 5 presentations is here. And I will ask Ruth to cover the research gaps. First,
okay, since our session included a lot about networks, so I split our gaps into operational gaps and research gaps on the next slide. So I'll try to go through this quickly. So for operational gaps, we need networking between international laboratories. So this would provide biodosimetry support in the case of a large scale exposure scenario. So we can help countries that have less, countries with high capacity can help those with less capacity. This would include calibration curve development, sharing blood samples of different radiation qualities, standardization and harmonization of methods. We also need to do interlaboratory comparisons. There are some going on, but there are some labs that don't have access to the ones that are ongoing. And we could do these comparisons using different conditions. And all of this will help maintain and improve the performance of members of the network. We also need to do more education and training, especially for new labs that are setting up, teaching them, methodologies, how to set up a lab, also for new methods that are being developed and for statistical analysis. We have gaps in the emergency preparedness support during emergencies, so we need to strengthen biodosimetry as a tool to guide medical treatment and integrate this into the national response framework. We also need to do some more work on knowledge sharing and communication, just to exchange information between laboratories, particularly from experienced labs to new labs. This can be done through conferences, meetings, webinars hosted by the BioDosimetry network, provide communication about upcoming meetings of interest, and get our website up and running. And then some countries require financial support for equipment, reagents, and training. And on the next slide, I have some more specifics about research gaps. So these are the gaps that came up throughout the talks, highlighting that any of these research gaps could be best addressed by international coordination of the research activities. But specific research that's required would be improving and validating methods for biological and physical retrospective dosimetry, particularly for protracted and chronic exposures, for combined exposures, to apply to clinical purposes, and the use of multi-parametric analysis. Also developing biomarkers for bone marrow and gastrointestinal syndromes, looking at markers for individual radiation sensitivity, developing and establishing statistical methods for dose and uncertainty estimations, and on the characteristic limits for more complex exposure scenarios, and also looking at long-term health risk studies following exposure with biomarkers and radiation epidemiology.
Thank you. Thank you very much. So for the session 7, we just concluded it, and each speaker mentioned what are the gaps and needs they have. So, and Adela already did a very nice summary. So I think we don't need to repeat this. These are Richard's suggested bullets. Then we have Adela's needs and gaps. We have 2 slides from Lake Eugene and 2 slides from Urna and from Evgenia Ostromova, of course. And finally, I want to bring back the slide which I showed in my presentation on the first day. These are some items where we would like to structure around our activities, and where I invite you as REMPAN network members to express your interest into contributing in some of these activities. We are very happy to hear that many of you mention mental health impact as areas of your interest, or something's already ongoing, or you're planning to do it. So I think there is a really nice room for collaborating in that area. Talking about risk communication also, it is extremely important, and there is something being cooking, but we also are interested in taking further, covering other areas. We also know that IAEA has developed recently a couple of good documents on risk communication in nuclear emergencies, so we may as well engage with the agency into some implementation activities. With the guidelines on internal contamination assessment and management, I really appreciate Chunsheng's work on preparing the background paper, compiling the experience with the accidents involving internal contamination, and that paper, once it's out, will be really used as a basis and justification for us launching the project on development of guidelines. We announced a call for consultancy for, we have some funds to develop a contract for updating the reports on stockpiles, which was published in 2007. And that call is still open until end of this month. And we have a number of applicants already submitted their requests. So we will be selecting someone and informing you in April. We really need to implement this work during this year because it is in our work plan, and we need to report to our member states about work conducted. And last consensus protocol on management on acute radiation syndrome, we heard an excellent presentation from Leif talking about where we are with this topic. It's a very large undertaking, and probably this year we will not be able to launch this work, but definitely for the next biennium we hope to include it in the work plan. And then there's been this long-standing aspiration to develop modular training material which could be used live or online, and which could be compiled depending on the audience, depending on the focus and topic of the training, which would cover all aspects of medical response and public health response to radiological nuclear emergencies. This we have not been able to undertake so far. And I know that many of you have excellent training programs. Maybe we could start from just inventorizing what is available and just building on whatever is already existing and not reinventing the wheel. And also with some of you, we discussed the development of information packages, fact sheets, and we really appreciate REACT's providing us a whole array of fact sheets on different isotopes, on the implications and risks and measurements and treatment. So this is a work in progress. We also want to mention again the need to translate WHO publications to UN languages. And I appreciate the work was already done by many of you, helping us to translate a couple of recent publications to different languages. So what we're going to do from here, how we're going to take this forward, the meeting report, including the draft research agenda, compiling all your input will be circulated. You will have a chance to comment in writing. And hopefully we will have a really nice product publication on REMPAN research agenda priorities. Well, this is my last words. Basically, I have not much to add, just to thank again all of you for connecting, for spending time with us, for contributing to this presentation. If you could all turn your cameras on at this moment, I would take a screenshot which will represent a group photo, what we used to have in the past. I think I will have to do it over several screens because we don't all fit in one screen. Oh, it's so good to see your faces. Oh my God, I missed you so much, people. Oh my God. We still have some people who still have not turned cameras because they stepped out, probably waiting for them to turn on their cameras.
Renat, I can't switch on the camera because it's written that it's abandoned by the host.
Abandoned by the host, okay. Let me do this, just stay with me, bear with me. I stop recording at this point.